Hello everyone. Good evening to all of you. Am I audible right now?
Yes, sir. Good evening, sir.
Yeah. So only 13 participants. Okay, just wait 1 minute more. Then we'll start the session.
Okay, sir.
Okay. So uh, this is the second session of for week 11. Let me present my screen. Then we'll start the session. Am I audible right now?
Yes,
Yes,
sir.
sir.
I just got disconnected. There is a technical glitch. Okay. So let me present my screen. Okay, so please raise your hand first. Let me know your doubt, and then we'll discuss or we'll do a summary thing.
Hello, sir.
Yes.
Sir, explain the transitive closure.
Okay. Okay.
Okay, sir.
Anyone else have doubt
Sir,
with regard? Uh,
the longest path.
Longest path. Yes. Last time we have seen with topological sorting. Today we'll see the longest path. Okay. And then after transitive closure, and then shortest path, and then the shortest path with another thing is Floyd Russell algorithm. That thing I will just leave for you to watch this session. That is, that is a big, that uh, finding the shortest path with not a single shortest path. That is a all pairs are shortest path, and that is discussed. It took 2 hours. Srikanth have discussed that, and it is in the, I think, in this session. So I hope please everyone uh, for that algorithm I will suggest you, because that is a session, and in that session the whole algorithm uh, in 2 hours it I have discussed. So I hope please watch that. It will be clear. And then we'll see the Prince and Kruskal algorithm. Yes, so this is one. In 2 hours, he discussed the Floyd Russell algorithm, SPG, SP1, SP2. So it will take more time. So that's why we usually keep this session with an example. It is a kind of tutorial, and slowly have discussed everything. Okay. So that part we will skip, and rest all like single source shortest path we will discuss, and longest path, and matrix multiplication, transitive closure, longest path, yes, and Prince and Kruskal algorithm. And this all source all source shortest path will try to, if you want, you can skip that also, all of you, because that is a big algorithm, and it is the question may not come. It is a kind of, you will sure that the question may not come. You can skip that adversarial algorithm. Okay. Am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Which one
So let's
algorithm?
start the. Sorry.
Which one
That
algorithm can I?
the algorithm is to find the all pair shortest path.
All pairs of this layered function.
Yeah, all pair shortest path. That what is that? That algorithm is Floyd Russell algorithm, I think.
Sir, I heard journal out, sir.
Yes.
Sir, but is the weightage for enter?
Sorry, weightage.
Yes, sir. But the weightage of enter.
So as a weightage, you can think 9, 10, and 11 will take 25% of. Okay, and rest even more than that, 28% I will say, and then rest all will be week 1 to 8, like this. And per week wise weightage I am unable to give, because questions may be in the mixed form. Even some question may be of, even in the single question may contain some 2 weeks concept. So week wise, given it will be difficult, yeah, like in the quiz wise, we can think that with 9, 10, and 11 have some weightage more than 20, more than 25 means 28, and rest all week 1 to 8 will have
most of the question from week 9 to 12 will be.
not most of the means that's why I'm saying the percentage why 25 or 28%. You'll think from integration, maxima minima, and global maxima minima, local maxima minima, and graph thing. 11 week 10, and then week 11 have some prims and Kruskal algorithm, longest paths, and then VFS, DFS, and that max minimum vertex cover. These things will come. Okay. Okay. That is called Versal algorithm. Versal's algorithm. And this all source shortest path is Floyd Versal algorithm. Okay, so let's discuss that longest path first. So let me take an example. With an example, we will try to understand that algorithm. So again,
Excuse me, sir.
yes.
In previous Open 7, we discussed the weighted graph, till weighted graph.
Sorry.
In previous open session, week 11, we discussed weighted graph, till weighted graph.
Not we not discussed weighted directed graph. We have discussed.
No, sir. Vishal sir taken the
Vishal,
class.
I guess.
Oh, Vishal have taken. Okay, and which? So what are yeah, that's one thing. So what are the
He di-
topics we have discussed?
he
Uh,
discussed the shortest path, Dijkstra algorithm,
Dexter.
and
Yes.
longest path, Dag.
Okay. Okay. So longest path he have discussed. Okay. And yeah, and
in
Dexter
shortest path,
Shortest
in
path.
and
Sir,
shortest
first
particle
method
source.
is discussed.
first
Yes.
method,
Yes.
it is discussed algorithm.
Yes. 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 Yeah. So let me jump to this. First
Yes.
these two. Minimum is cost is spanning tree. This one, Prim's and Kruskal algorithm.
Okay, sir.
Let's discuss this one. Then we'll back to this all where shortest path will skip. Okay, that will be, I will again say to watch that session. It will take 2 hours to understand that. So if you watch slowly, everything will be clear. And it is a kind of computation. And in that, tutorial, that is a tutorial, and 2 example have taken by Srikanth and have discussed all. Yeah, so let's discuss first the Prim's and Kruskal algorithm. Okay, so
Dijkstra algorithm completed. We have discussed Dijkstra algorithm.
yeah, in the last session, I think we have discussed Vishal, right? The extra algorithm.
Yes, sir.
Okay. So first thing is Prim's algorithm is, suppose we have a graph and this is a weighted graph. The weight could be positive, negative, anything. Okay. And what is the first thing is what is a tree? So tree is also, you can think, tree is also a graph. Yeah. Okay. Tree is also a graph, but it has some property. The property is that we will think for the undirected graph here. As you know, undirected graph will think. Okay, so graph will be undirected. Okay, and it will not contain any cycle. Okay, the tree is one thing, a graph. Okay, suppose you have a graph. I'm making like this. Suppose these are the vertices we have.
Connected graph.
Sorry.
Minimum connected graph.
Another definition is minimum connected graph. So tree is a connected graph. Okay, it will not be disconnected. It should be connected, first thing, and it will not contain any cycle. The definition of tree is simply is that it will not contain any cycle and it should be connected. So if suppose you have a graph like this, okay, so if you see that this is not a tree, the reason is this is a cycle in the graph. And another property is of the tree is the number of, there is a relation, that number of, suppose a graph have n vertices. Okay, a graph have n vertices, so number of edges is, how much edges it have? It will have, if it have n vertices, then number of edges will have n minus 1. N minus 1 edges will be. This is one property. If it have n vertices, then number of edges will be n minus 1. So simply definition is of a tree is a connected graph which does not contain any cycle. This is the definition of tree. So minimum cost spanning tree is, this is one tree definition, and spanning tree. There is another word, is spanning tree. So what is a spanning tree? Spanning tree means it will be a tree, and spanning means suppose if you have a graph. Okay, I'm just making like this. Okay, this is the same. Okay, suppose this is a graph. So this is not a cycle. So what we can do, we'll try to find a tree. Okay, we will try to find a tree. So this is a tree, as it is connected and it is not containing any cycle. And it is called spanning tree. Means spanning means it will be a subgraph. See that the number of vertices are same, the edges are whatever the edges, connecting edges are there, but we'll try to remove that edges which is making which one is making a cycle. So this is a tree, and if you add this edge and this edge, this will become the exactly whatever we have this graph. So
Largest
spanning,
cycle, sir.
sorry.
We will remove the largest cycle, sir. Means if it was like 6 and 5, if it is facing the frame, we will remove the largest one, sir.
Largest, sorry.
In terms of the numbers, sir, the weightage of the means
No,
I'm
so
saying like there
I'm
was
just saying the definition of, yeah, that is one thing, that is an algorithm, no? But I'm saying what is the spanning tree first, then we'll back to the
okay,
minimum
sir.
cost spanning tree. But I'm
Okay,
just
sir.
explaining what is a tree, then there is another word is spanning tree, and then minimum cost is still remain. There are, it is like
Okay,
minimum cost is spanning, there are 3 words, minimum and cost. There are 4 words, minimum cost, sorry, 3 words, minimum cost and spanning tree.
okay, sir.
Okay, so what is the spanning tree means? It will be a tree and it will be a subgraph of this one. So see that if you remove these 2 vertices, so it is a tree, and if you add whatever you have removed that, then you will get exactly the same graph you will get. So means that is a tree, means it will be a graph. The spanning tree will be a graph and it will span the whole graph. It is actually generated by this graph, which is a tree. Okay, so this is the meaning of spanning tree. So a spanning tree is subgraph which generate the whole graph. That is the meaning of a spanning tree. Now there is next word is minimum cost spanning tree. So this is one word. These two are different word. Like we have seen the tree. What is tree? What is spanning tree? Now, what is the minimum cost spanning tree? So suppose this graph we have. Now this is, we'll back to our weighted graph, as this is a weighted graph, and it does not, there is no mean to say that it is a negative or positive weight. There is nothing here, is not a kind of index star. We don't have any negative weight, but here it is allowed for both Prim's and Kruskal algorithm. Okay, and now we have a weighted graph. So we'll try to find the tree, even not tree, spanning tree, which have minimum weight. That is the meaning of minimum cost spanning tree. So once again, we'll try to find a tree. So as here, we'll try to find a tree. This one is a tree of this graph, even not only tree, spanning tree. So similarly, for this graph, we'll try to find the spanning tree. So first thing, let me note again that for a graph, you have many different spanning tree. This is one spanning tree, okay, of this graph. There could be another. So this is one, another one. This is another one, which is also a spanning tree. This is a tree, and actually we'll just add this edge, and this edge is to become the whole graph. So this is another spanning tree. So for a graph, there are not even infinite, but finitely many spanning tree could be possible. But we'll try to find that spanning tree which have the minimum weight. So from here, we have a weighted graph, okay, this one. From this graph, we'll try to find that weighted graph which have minimum cost. Not only the weighted graph, minimum spanning tree which have the minimum weight. So how we can find that minimum cost spanning, that which have the minimum weight? How to find that spanning tree? So for that, there is two algorithm, Prim's algorithm and Kruskal algorithm. So these two algorithms are totally different, but whatever you will get the spanning tree, minimum cost spanning tree, the weight of that spanning tree will be the same. By both algorithm, whatever the weight you will find for that spanning tree, it will be the same. Yeah, their structure may differ. All of your understanding, their structure may differ, but their weight, calculated total weight, will be the same of that spanning tree. All of your understanding or not?
Yes, sir.
Okay. So
Sir,
let me discuss.
Can you repeat what I mean once again? What is the difference between a tree and a spanning tree?
So tree could be anything, like this is a tree. So spanning tree. So trees, trees. The definition is mean to say a tree is a graph which is connected and does not contain any cycle. But spanning tree is needed for the spanning tree. You should have a graph like this one. Okay, you should have a graph, and from this graph we'll try to find a tree which is actually a subgraph. That's the meaning of spanning tree. So suppose this.
That graph has no cycle.
So this is a this is a subgraph of this one, right? Number of edge where vertices are same, the connecting edges is also same, but it is not that this edge is not in this graph. But so this is a tree, and we will say this is a spanning tree. The reason is number of vertices are same, edges, whatever the edges are connecting the vertices, that is also same. Only some edges are not there. So this is a spanning tree. There is another spanning tree could be there. So in a tree, number of vertices will be the same. Okay, that is spanning tree. See, this have the number, whatever the number of vertices. This one also have the same vertices. Edges also, whatever the connecting edges are the same. Only less number of edges in compare of this one. This edge is not there for this graph. But this is a spanning tree.
There could be multiple spanning tree, right?
Yeah,
example,
there could be multiple.
I can have a spanning tree with only one edge removed. I can have a spanning tree with n minus 1 edge removed.
Yes, this is another spanning tree. Okay, so let me erase it. This is another spanning tree. Number of vertices, if you count, the same. Edges are whatever the connecting edges are same. Only the some edges are not there, like this one and this one.
Okay.
So that's the meaning of spanning tree.
And minimum spanning tree
Which
is
is
the one
which will be
which
a
has a lower
tree.
weight.
So there are, see, this one there are three. We are able to see there are three spanning tree. Now suppose I am giving some weight here. Suppose here weight here is 1 and is 1. Let's say the different. Let's say 3. This weight is 4 and this is 2. This is -1. Okay, so this is one graph, and so now this is one spanning tree. I am saying so same weight will be come here, will be implemented here. So this is 4, this is 2, and this is -1. And what is the weight? If you count weight, this is 5 to 7, 6. Weight of this one is 6. Let's count for this one. This is 3, 4, 2, and here is -1. So now let's count the weight. This is 7 to 9 -1. The weight is of this one is 8 of this graph. What is the weight of this graph? This is 3, this is -1, this is 2, and this is 2. So this is again 5, 7, this is 6. So see that there are 3 spanning tree we have, and with the different weight. So what is the minimum cost spanning tree going to be? Minimum which have the minimum weight. So this one have minimum weight, this one have minimum weight. So these two trees, spanning tree will be, you can say, minimum cost spanning tree. Even suppose I am saying the weight of this one is become 7. For the instance, I don't know if if I will change here the weight. Let's say this is 3. Now it will become 3 now. So now the weight become 7. Okay. Now which one is going to be the minimum cost spanning tree? So only this one. So this spanning tree have the minimum weight. So this one is the minimum cost spanning tree, MCST. Is that clear?
Yes.
Yes, sir.
Now, but this is, see, what I did here, I draw the spanning tree all possible. Even I don't know what are the other spanning tree could be possible. Okay. There could be lesser than 6. I don't know, but I draw 3 and I compare in this 3 and I said this is the minimum cost spanning tree. Maybe it could have lesser than, I don't know. So what is the algorithm? What way we will try to find the exactly minimum cost spanning tree? So for that, there are 2 algorithms. One is Prim's and another one is Kruskal. Okay, and both are in algorithm wise, as they are different. Okay, so let's discuss the Prim's algorithm. Okay, so what is the Prim's algorithm? So I'm taking for this is an example I'm taking. Okay, and so what is the Prim's? Prim says the algorithm is, this is the graph we have. Take the edge, start with that edge, okay, which have the minimum weight. So which one edge have the minimum weight?
AB.
A, B. No. EF also right there.
Okay. Yeah, BD, CF.
No, EF is -6. That is
Yes,
very
EF,
less.
sir, EF, -6.
EF is the minimum one, right?
Yes, sir.
Okay. So take this edge. Okay, I have taken this edge now. Now I will start growing. Okay, growing means I will start moving which have the minimum weight. I will start moving with that edge which have the minimum. So I took this edge. Okay. Now I will see this vertex and this vertex, and I will start moving that way which have the minimum weight. Okay. So which edge have the minimum weight in compare of connecting these two vertices? A, right? So I will choose now this edge. Okay. Now what I will do, again I will start looking with these three vertices, and I will see the connecting edges which have the minimum weight. So which one have the minimum weight with connecting these three vertices?
We have two options.
There are two options we have. So any one of we can choose. There are two options we have. Either we can choose this one or this one. So I'm just choosing this one. Okay. Now we have 4 vertices, and I will start doing with that which have the minimum weight. So now I will move like this. I will took this edge because this is -4. Okay, now I am moving ahead. Okay, I'm doing the fast. Now in compare of this one is, I will not, now there is one concern that I will not take this edge. Why? The reason is, if I will take this edge, this will become now cycle. Right? This will be a cycle. B A or A E A, D B. It will become a cycle. So I will not choose this edge. Okay, because of this one, it will be a non-tree. It is not a tree, but we want a tree. So I will not choose this one. Except this one, I will start moving now. Choose the minimum with the minimum weight. So this have the minimum weight. Okay. Now this is now which one have the minimum? So this one and this one. So I will again not choose this one. The reason is it will make a cycle, and also it completed the all vertices. Now once I choose this edge, it is actually completing the all vertices now. Okay, so this is, we have the tree we got. Okay, and weight are okay. This is the weight. We can count the weight here. It will have negative weight. Okay, now this is 8. This is -12. This is -9 weight. I don't know what is in this graph. To see that, I think.
Sir, can you explain again that?
Yeah, I will again explain that.
Sir, if there was an option to choose between -6 and -2, we must choosing -6, sir, because -6 is a less than -2. Like
Sorry.
Like there was a condition to choose between -2 and -6. We must be choosing -6.
Yes,
Because it is
because
smaller
this
than
is the minimum number, right? -6 is minimum in compare of -2.
-2, right?
So I will choose first -6, then then if it is lesser than -2, then also I will choose that. Otherwise, -2 will choose. Okay, so this is, see that this is a tree, right? This is a tree with the minimum weight -9. Okay, let's see another weight is there. We skip this one, no? So what I am doing, I now erase that, and previously I, between two options, this one and this one, I choose this one. I choose this one. Now I am choosing this one. Okay, so this one this one, and then with the minimum this, and with this which have the minimum this one, and also it is completing the all vertices now. So now we got this, this, and then this.
In this case, our answer is also -9.
So it have also the same weight. It will contain the same weight. So minus 6. Now count this. This is again 12 minus 9. Okay. These two are same. But yeah, see that structure wise, these two are different. But weight are same. Okay. So this is the Prim's algorithm. So Prim's algorithm is you will start growing your tree with the minimum weight. As here, I first started, I choose this with the minimum weight and then start growing from here. So how I started growing, which have the minimum weight. So then after I choose this weight, then which have the minimum. So I choose now this one, then which have the minimum in compare of connecting this vertex, this vertex, this vertex, and this vertex. So this is the minimum one, this one. And then again with connecting these 5 vertices, which have the minimum weight, this one. So now also it complete the all vertices also. So we'll stop now and we'll count the weight. Okay, this is the Prim's algorithm. Now let's see the Kruskal algorithm. What is the Kruskal algorithm?
So it's like writing all of the edges in ascending order and choosing if the graph is completed or not, if all the edges are covered or not with that ascending order of the
Yes.
edges.
We'll write the edges in the ascending order and we'll start choosing with the minimum weight and we'll
Yes,
connect.
right.
Slowly it will be connect. So see how
yes,
it
if
could
we
be.
connected with,
So yes.
it could be like let's just first write the edges, all the edges A, B, B, C, C, D, E, D. First, we will write all the edges and we will assign the weight of those edges and we will write it in an ascending order. And once we write it in ascending order, we will mark those edges. If we have gone before that before we have reached that edge before with an minimum weight, we will not write the again that edge. Like if we reach A to B in with the weight of 1, we won't be writing it somewhat like A to D we have actually -4, so it was a minimum. We will not write E to D. It is 1. -4 is lesser than 1, so we will not write E to D.
Yes. So yeah, let me complete now. So here itself, while writing the E of all edges, let's see it here. So how we can do it here? So Kruskal says, first choose that edge which have the minimum weight. So I choose this edge. Okay. Once I have chosen this edge. Okay, my work is done for this edge. Now I will accept this one. I will start looking that edge which have the minimum weight with the other, like except this one. So now this edge is the minimum weight now. Okay. After these two edges, now I will start again looking which have the minimum weight edge. So we have now with -4. Now we have this one. Okay. In pieces, see that the edges are actually in pieces. And we are actually, I am just collecting those pieces. Okay. And slowly, once you will see, once I will choose the all vertices or connecting all, not all vertices, once I will done with the choosing edges, which include all vertices, then we'll stop and then it will, then after you will see actually it will be all vertices will be connected slowly, automatically. Once slowly you have to choose with the minimum weight edge. So after choosing this one, now choose rest all which have the minimum. So this one have and this one have. So any one of the one you can choose. So I'm just choosing this one. Okay. Now compare with that, you will choose that vertex which have the minimum weight. Again, you will not choose this one. The reason is it will, once you will choose this one, it it will make a cycle. So I will not choose this one now, except this one which have the minimum weight. So this one, and this one we have on this one. So in this 4 to have the minimum, so I will choose this one. So slowly you see that in the piece wise I will started choosing, and slowly you will see that actually this is connected tree you will get. And with the same, if you count weight, this is going to be -9.
Sir, can you please explain this process once more?
This is not -9. What is that? -9. Yes, there is also -9. Okay. So what is the process again?
So it could be best that if you write all the edges and if you write those values, it will be good to
Okay.
understand.
So I will, okay. So I will choose this. Okay. So what we can do, the process is, we have to choose edges, okay, with the minimum weight, sorry, with the A weight in ascending order. So this is -6, and then next is BD with -4, and then next is A is there with -2, then after -2, 1. Okay, so AB is there 1, then ED is there 1. Now BC is there 2, then CD is there 3, then BE is there 5, and then DF is there 6. So I just wrote the all edges in ascending order. Now what we can do, I will start choosing the edges which have the minimum weight. So once I choose this one here, so anyhow we have to look at the graph. Without that it will be difficult. Okay, it will not be difficult, but you have to very clearly, you have to observe that whatever the vertices here is becoming, no?
Reach it. We should not reach it again.
So here it should not be like, it should not be form a cycle like that. We have to choose. So if it is here some fixed or even no lesser edges, then we can directly do that from the graph. Okay. So as here, if you see it here, I will choose the minimum. So this is, ascending order. This is in the ascending order. So this have the minimum. Now this edge I have chosen this edge. Then after I choose this one. Now A is the minimum. Then I choose this one. Then there are two, AD and B. AB and ED. Either let's choose this edge. Once we choose this edge, then I will start choosing the same, then it will form a cycle. Then we will not choose, then we will jump to the next. Now BC is there. And once we chose BC, now rest all, if any one of the edge will choose, then it will form a cycle. So now the spanning tree is going to be this, and then this. And if you see the weight, it will again the 9, -9 will come. Okay.
Yes, sir.
we
Yes.
also so
Mm-hmm.
we also find that stemming tree without seeing the graph with the help of edges like readiness below the graph EFVD. Only given that EFVD and its weight, then we do not need to check graph.
Sorry, without giving the graph, we will try to find.
Yes,
So anyhow, it will this one at least given, right?
yes.
This
Only
will be.
weight, only weight and vertex is given, like line
Mm-hmm.
EF and VD.
Mm-hmm.
It can
So
possible.
yes, yes. So that's the way we'll actually once you will start. So these algorithms are actually for the computation, like writing the code in Python. So for that, some algorithm will we have to create so that it will not form a cycle. Otherwise, if you able to direct the graph while in the manually we can, if we start do, then we'll try to graph, and from there we'll see that is there any cycle becoming cycle or not. If it is cycle, then will not choose that edge. Otherwise, anyhow, if it is in this fashion it is given, then you have to be good coding, even no, you have to write a proper algorithm in coding format so that it will rectify that it is not containing any cycle. In that format you have to code. But this time I don't know how you code this Kruskal algorithm in Python. Okay.
There is a questions on there. We have to code for this for
Sorry.
Pushkas or for
Sorry.
every this graph theory.
Mm-hmm.
I haven't seen any question of in Python on this graph theory.
No, I think in CT we have no some graph theory. Then Python, I don't
Right.
know there are some
Just
question or not. In the next, when you will start in machine learning later, you will see there are some, machine learning algorithm
No, this
which have.
whole graph tree is a part of the data structures and algorithms.
Yes.
So
Yeah, we are
you'll
having that in CT, sir. Today only we have
exactly
studied the BFS and the DF.
Yes. Yes.
right.
how you are doing CT and Python both at a time? How can
So in machine learning, there is one algorithm. I don't know what is that. That algorithm in machine learning which uses this BFS or some graph theory concept. To find as for the work machine learning to form a machine learning algorithm. Some
It
algorithm is
is,
there.
yes, sir. It is a bit complicated, but I guess with time we'll know.
That is that tree farming. There is that algorithm is used. That algorithm is machine learning algorithm that uses a tree format. It will form uh, whatever so that I have seen that you will get a you will train your data set with the fix. You will get a data set, and what you can do, you will break your data set in two part, and you will again train your data set, and again you will break in two part, then again you will it will be a kind of tree. So you will train your like this, you will make a part of your training data set. Okay, and then it will form a tree, and some basic concept of tree will be used there. Some name binary search is there. Yeah, some name is there. I am not till now. I have seen once decision tree. Yeah, something is there which uses the graph theory. So that's why we can, here we are extending not only the, the graph in more graph theory is some different. Here we are in graph theory here in maths one, we are studying algorithms. BFS, DFS, finding the longest path, shortest path. But graph theory have some more, planar graphs, Euler formula, there are different more. If you go more in deep graph, there are very different. There is one book, D.V. West book is there. These algorithm will be come in later. So before that, there are some graphs are special graph, which is called bipartite graph and a complete graph, and other graphs are there. So many concepts is there in the graph, but here we are just listing the algorithms for the purpose why it is so to use in the, data in machine learning or in Python. Python is just for that is a language you have to learn. Otherwise, machine learning will see some this graph theory algorithms. Yeah, Tharva, I have some doubt.
Shubham sir, have a doubt in last week, week 10, little doubts.
What SG and
10.6,
GSH? Yes.
activity 10.6.
Okay. Okay. Now, well, back to so let me discuss that activity. So, activity 10.1.
10.6, little doubt, sir.
What is that doubt?
Actually, uh, I understand the concept of BFS and DFS, but there
Mm-hmm.
are some two questions. Second question, yes.
Mm-hmm.
Which of the following cannot be age in original graph?
So how
Right?
we can do this?
Huh.
We obtain the following DFS tree root at node A for undirected graph with vertices this one. Which of the following cannot be an edge in the original graph? So BF will be an edge, or AG, A and G, this one, EF, this will be an edge, or AF, this will be an edge. Which of the following cannot be an edge in the original graph? How we can get this? Anyone?
That is a rule like in DFS.
Mm-hmm.
In DFS, in we have any edge in any levels in the same branches.
No, that is for the BFS, no? For
Yes.
DFS, for BFS, if you have two different level, no, means if there is one different level, then
I and
So
I plus.
in
Yes, sir.
BFS, we have edge in I and I plus 1. But in BFS, we have any edge in any levels in the same branches.
So
Yes,
EF,
no
is-
as
EF is not.
different with branches. We do not connect edges to different branches.
sorry, could you repeat, please? I'm not getting.
Into different branches, we could not connect with both.
Yes. In two different branches, they cannot be no edge
Connected.
between two different branches. If it is
Yes, yes.
if it is there is an edge between two branches, then what will be in that? If suppose I am saying, suppose there is the edge between E and F, then once you reaches with the algorithm, no DFS, so once you reaches F or once you reaches E, then
We
okay,
will,
if there is a edge between E and F, then you will move to EF, right? Because there is
Yes.
this
yes,
unvisited vertex is there. F is will be if you reaches to E and they start looking your neighbors or connected vertices. So F is going to be new vertex. Then you will go to F.
Yes.
So between two branches, there will not be any.
Connected edges.
If it is
sir.
edge, then if it is edge, then it will be connected. But if it is in the same branch, there is a possibility that could be an edge. The reason is if you are suppose from A you started B, then D, then F. If there is an edge between A and F, then you cannot connect in the DFS tree. The reason is you have already visited that A. From F, you have already visited A. So that's why you should not connect that. And yeah, it could be in the original graph, it could have that edge. What I mean to say, are you understanding? All of you are understanding or not?
Sir,
Yes, sir.
What I mean to say, let me repeat again. Once I will take the here.
सर हिंदी
Suppose I
में
am saying,
समझा दीजिए, सब लोग समझ जाएंगे.
sorry.
sir.
You can explain in Hindi, everyone get the answer.
Yeah. Okay. That is, yeah, we can do. So I mean to say, suppose I am saying there is an edge between these two, okay? Between A and F. You started this is a rooted at A, right? That means you are starting your algorithm from A, okay? Now, what you can do, start as, DFS is exactly searching on Chrome, internet. So you started from A, okay? I reaches to B unvisited vertex, okay? From B, you will start watching or unvisited vertex, which is E, and E is there and A is already visited. So either you can move this one or this one. Okay. Suppose I move to this one. Okay, at E. Okay. At E I moved, I visited and start exploring E. Suppose there is an edge here. Okay. Then unvisited vertex, what will be unvisited vertex? It will be F, right? From E, I can visit F. That means I can move to here. But this is a DFS tree, no? There is no edge in between. That means there is no edge in here. There is no edge. Otherwise, if there will be edge, then from E, I move to F. I should to move to F. But there is no edge. That's why from here, I have to back B. And then from B, I started D and then D to F. That's the DFS. Correct?
Yes.
Get it?
Yes, sir.
And from F, if there is an edge, see, this is a possibility, right? Because the reason is from F, I can visit D here. I can visit D and F, but I cannot go any one of. I will backtrack because these are already visited. These is already visited. From F, this is already visited. So that's why there is a possibility that could be an edge, but there is no possibility between two branches here. Please, all of you, mute yourself. Some dog is barking. Let me mute. Okay. So this is the reason why it is between two branches. There is no edge because of this algorithm. Algorithm says if there is an edge between E and F, then once you started exploring E, if there is an edge between E and F, then you will start exploring from E, F also. But in DFS, there is no edge given. That means you are backtracking to B and then from B you are reaching to F. That's why there is no edge in the original graph. But there is a possibility in the same branch. In the same branch, there is a possibility there could be an edge because you are coming from here, and then here, then here. Then from F, you are backtracking. If there is an edge, you can directly backtrack here, but there is a possibility it could have, but there is no mean. You are backtrack and then again backtrack to A, then here, and this.
Sir?
So in general, can we say that in DFS, it is not allowed to jump from one branch to another?
Yes, in DFS tree.
Yes.
In tree, this
But
problem
there
is
is
for
a-
tree.
DFS tree, DFS tree. Yes. But the same is allowed in the BFS, is it?
Yeah, in the BFS there could, if suppose this is a BFS tree, okay? If this is a BFS tree, so what is the label? You can mark here label easily. This label is
one
C.
level.
This is one label, okay? And this is two
Okay.
label. These are at the 2 level, and this is at the 3 level. easily you can mark, and in the same level there could be a edge in the
So it's
same
like
level
we
and one
can
level difference. Why? The reason
No,
is
no,
in the
no.
same.
The question is from E to F in the BFS, will there be possibility of an edge existing in the
Yeah, in
BFS?
BFS there is a possibility.
Okay. So in summary, we can always say, right? In DFS, there cannot be an edge between different branches, but in BFS, it is possible.
It is only
Yeah.
possible then it is I and I plus 1. Only second
Only
last
single, there is one increase.
yes.
One level,
Like
you mean?
yeah,
The
like A to C, we can go A to B, we can go. We cannot go A to G, A to E, A to D.
yes, there
No,
is
but A to B already there is an edge, right?
No,
A
no,
to
we
B
can
will.
go. If it the question like was like we there is edge between A to B. Yes, there is a edge because we can go one step, but we
If
cannot go A to B.
if another edge connected with F like
So see that
S,
the simple thing is that if the level difference is greater or equal to 2, see the level difference between A and F. There is a level difference which is 3. So if level difference is more than 2 or 2, then there will not be any edge. If level difference is less than 2, either it could be of the same level or there is level difference is 1. As here, the level difference between E and F is what? 1. So in that case, there is a possibility in BFS that could be an edge.
yes.
You will once, but if you will say that there could be an edge between F and C, then this is not true. Because see the level difference between these two is 2. And so why this is the reason? Can you tell me why this is happening? Why I'm saying if level difference is 2 or greater than 2, then there is no edge. Why? What is the reason?
Sir,
That,
if label is same, then it may be possible there is a age.
yeah, if the
Yes.
label is same or label difference is 1 also, then there is a possibility that could be an edge.
Then if there is a age between D and E, then what is the need to come back and go
Sorry,
for E?
I didn't get.
Sir, I want to
Hmm.
say,
Hmm.
if there is a age between E and D,
Hmm.
then why we come back to B and create another branch for E?
Because of because of Q. If there is an age between F and B are saying no. The because of
No,
if you
no,
see the
sir, no,
algorithm,
sir. Sir, D and E.
B and E, this one,
No, no, no. D and E.
D and
D
E,
and E.
this one.
Yes, sir.
Yeah, so D and E is why? Because if you see that the Q, no, if you remember in BFS tree Q, in Q, what is that Q? First come, first out. That is, BFS. If you
Yes.
start doing
No, no,
rooted
sir.
here,
Sir, I'm talking about DFS.
sorry.
I'm talking about DFS.
Oh, DFS. So in DFS, yeah, in DFS, why it is not? Yeah, okay. I will back to.
There,
Okay, let me complete the first BFS also. Let me complete the BFS, and in the DFS, if there are in two branches, then there is no age in between. Okay, this is the DFS set.
yes,
Because
yes,
this
sir.
one is a different branch, this one is in different branch. So in DFS there is no age. But I want to talk to in the BFS. I'm just discussing BFS. So in BFS, why it is so? If you remember, the Q first come first house is there. What is, suppose you started your algorithm from A, okay? You started your algorithm from A. So, and there is, there is a edge in these two, okay? So you will write like this, and then once you remove that B, then visited vertex are B and C, okay? And then you will start exploring B first and then C and then rest all. So once you started exploring B, you will remove C, then C will be here, and unvisited for B, what are things will come? D and E. So here is after, here will be D and then E will come. And after completing B, you will back to C here. That's why they at the same level they are coming. So we'll remove that C. Now they will shift to here. It will shift here, this will shift here. So with the whatever the level wise it will be go.
Sir, in BFS, if the levels are same, so we can draw the edge
Yes.
between them.
Yeah, so you can remember, so because of this algorithm property, if the labels are same or label difference is one,
okay.
then there is a possibility there could be an edge. But if label difference is 2 or greater than 2, then there is no edge.
But in BFS, direct backward graphs, direct backward edges cannot be there present, na?
Backward edges will not be there.
But we can draw edges one side to another side.
One side not. So simply need, if you are just to remember, between two edges, between two branches.
Branches. Yes, I am trying to say.
Yes, there could not be any edge.
Okay.
By this way, you can remember in DFS between two branches there could not be any edge, and in DFS if level difference is same or level difference is 0 or level difference is 1, then there could be an edge. If greater than 2 or 2, then there is no edge.
Okay, sir.
Same, there is edge, na, sir?
Sorry?
If level is same, there is edge.
Yeah, level is same, then there is an edge.
So please discuss or test because
Different, but branch should be different.
But branches could be differ in the DBFS. There is no mean of discussing in a branch in the BFS.
Yes.
In DFS there is a meaning of branch, otherwise in DFS there is no. Okay, so let's move to next is the shortest path. So there is first thing is transitive closure, then shortest path. Okay. We'll see the transitive closure. So for with examples, so just keep a minute, okay, just a minute. So first we'll see the transitive closure. So there are first thing, what is a transitive closure? So suppose you have a graph, okay? Let's understand first what is the transitive closure with the graph, with the simple thing. Then we'll see the matrix multiplication, and by that way we will try to find the transitive closure. Okay, suppose I am just making a graph. Okay, this is A, this is B, C, E, F. Okay. So what is the transitive closure of a
It's
graph?
like a matrix.
Sorry?
It's like a matrix. Like there is we will write in a matrix form, sir. Like A
Yes.
to A.
Yes.
If there is A, we will write 1. If not, then we will write 0.
So that thing we can find the matrix, we can find, that's fine. But for what is the transitive closure meaning is that the simple is, see, you know, between vertex A and E, is there any path?
No.
E and
A and E.
Direct
there
is
is
not. The
path
path is
between
A D Y A
Yeah,
D
there
E.
is a path, no? There is a path, this, by this way you will go. A
Yes.
to D and then D to E. And there is
Another
another
path is
also.
also. Yes. A B C
A,
D.
B, then C, then D, then E. So what is the meaning of transitive closure is, if between two vertices, any two vertices, okay, between any two vertices there is a path. Okay, so transitive closure is what? Transitive closure is a graph. It is a graph. It is a graph, okay, with the same vertices. Okay, I'm just writing, okay, I'm writing the vertices here with the same vertices. Okay, this one, this is the same number of vertices I just wrote here. Okay, so what I will do, so this is I'm saying this is a transitive closure of this graph. Okay, so what is that? See, what I will is do, between, see that between the vertex A and E there is a path, right? The path is this one and this one. So what I will do, I just wrote here the vertices. I have seen that there is a path in between. That means I will draw an edge connecting these edges. So this is A, this is B, C, D, and E. So if there is a path between two edges, then I will connect that, sorry, between two vertices, then I will connect those vertices. See that as previously. So before that, first thing, just same graph, let's draw the same graph. Okay, first draw the same graph. Okay, now I have seen between that A and E there is a path, then I just connected here. I just draw a graph. Okay, now there is a path between the vertex A and C, right? This path, this is a path between A and C. So if there is a path, let's connect this. There is a path between between A and D. Yeah, already there is a edge is already here. There is a path between A and B. Yes, in the same edge they are actually connected. Okay, now C is just now I connected with this edge. So A is done. Let's take B. So one by one we will do. Okay, let's take the vertex B now. So there is a path between between A and B and E, right? This vertex and this vertex. What is the path? The path is this one, and then this one. From B to C, C to D, and D to E. So there is path. If there is a path, let's connect that. Okay. Now check the others. Between
B
B
to
and
D
D,
also.
have the path also. So let's connect that. Okay. And all others are already with an edge connected. So that's done. Now let's check C. Okay, now let's check C. So already A and C. So I will talking here only. I'm just looking here because this is we are constructing. So A and C. So yeah, this is a path, this way and then this way. So that is then is an edge. So which is already we have drawn this one. So there is no issue. And B and C already D have. Okay. So there is a path between C and E. So that means let's connect that here. Directly connect. Means there is an edge between C and E. And rest or compare, it is already connected with an edge here. And let's move to D here. So D between except B, all are connected. So and already we know there is a path between B and D. So that means let's connect here. So as already it is connected. So we are done. D is already done. E is also already we have checked with all vertices. You can see already you can see that A and C there is a path. So it is already we have matched. And then after B and E already we have matched. So that means we got this graph. So what is the property of this graph? What is happening here? This is a kind of we are completing the graph. So what is the transitive closure of a graph? A graph, if there is an edge, then we will connect that. So this is a transitive closure.
If there is a path between A and D, then connect direct A's A and D.
Direct edge, yes.
Okay.
So this is the transitive closure of this graph. This is the transitive closure. Suppose I'm just making another graph, okay, with this very similar same, okay, exactly same I will say A, B, C, D, E, but extra edge I'm adding here, which is F, and it is alone. And I will say that what is the transitive closure now? Or even let's say I'm just removing now this one and I connected these two. So what is going to be the here now transitive closure of this one? So what you can do, you with the same graph you have to draw. Okay. Now we'll start again thinking if there is a path, then we'll directly draw the graph. So there is a path already between A and C. So that means I need to draw this one and this one. And this part is done. But there is no path connecting to A or E or B or any vertex with E and F. So the transitive closure with whatever this one we have, this is exactly this is. If there is a path, then we will connect. If there is no path, then we will not connect. That's all. And
Okay,
this is
so sir, if the graph is connected, then every vertices will be connected to the other vertices
yes,
in transitive closure.
yes, in transitive closure.
Sir, can you explain again that?
What do we do? What do we do with this transitive closure?
Sorry.
What do we do with this transitive closure? I mean, what does it depict?
So it will be used, a transitive closure is, shortest path it will be used. Single source shortest path or source shortest path. There we will see the path
like BFS.
No. Transitive closure will be used in shortest path. And what is in the shortest path? And what is in the shortest path? Like there is, path of length 2, path of length
Sir,
3.
sir, yeah, how
Yes.
can we from transit to go and find the shortest path? Because there is no way to.
In this, there is no way. So shortest path, so there is in shortest path also,
How
in
come
terms
we
of,
get?
uh,
Yes,
in
I'm asking.
terms
How can
of,
we know that?
if suppose your graph is unweighted, okay, there is no weight on the graph. So, but what is
Yeah.
going to be the shortest path in that case?
Mm,
So there what is that? There we will we will do with the uh, length with shortest path with length 2, shortest path with length 3. Okay, so what is that algorithm is extra is there?
No, in
Like,
transitive, what we are trying to do, sir, here, as I see, if you don't have a direct path to a vertex, okay, but if you have an indirect path, what we are depicting as a part of transitive closure, we are depicting a direct path in the graph.
yes, yes,
That's the only thing, right?
yes.
Sir, can you explain again the properties of transitive?
So there is no property with there is no property. Mean to say, if you have a graph, then what is the transitive closure of a graph? Means exactly finding the another graph. And what is that graph? We will connect those vertices if there is an path between these any two vertices. Okay, if there is a path between any two vertices, then
Okay.
transitive closure is the updated graph. And what is the update in that? We will add those vertices if there is an edge in our previous, like here there is a path between A and E. So
Hmm.
there is a path A and B. So in the updated graph, we just connected that.
Okay.
This is the updation we are doing in the transitive closure.
Okay.
There is there is a path between A and C, right? This edge and this. So
Hmm.
what is update we are doing? We are just connecting this edge. We are adding
Okay.
this. This is the update we are doing.
If there is a path in B and C, then
B and
we
C. So already in the same edge is there. So there is nothing because the edge is already there.
yes we okay.
So if there is an edge already, then that's why I am saying the same. First you will draw the same graph and then you will start updating.
Okay. So I have some doubts in week 9. Can
Okay.
you take that doubt?
So let me finish the graph thing. Okay.
Okay,
Then we'll
okay.
discuss. Okay. So this is the
sir,
transitive closure. Yes.
and explain the standard closure once. What I
Sorry.
could
Oh,
not understand. In the standard closure, sir,
uh-huh.
once you explain it again. Yeah.
Okay. So let me draw with the different.
Has like we use Prim's algorithm and Kushner algorithm to find the minimum sampling tree, and like float washer is used for the negative graphing. We can find. So, what is the use of transitive closure? What is the
So what
specification
is
of
the
this?
use of transitive closure? So use of transitive closure is in finding the shortest path. And you will see the in the Floyd Versal algorithm, that is transitive closure is mostly what is the Floyd Versal algorithm. Let me show you first.
Have you discussed Floyd algorithm already?
Yeah, it is actually in the Floyd Versal algorithm. Floyd Versal algorithm is updated of transitive closure update. There is some extra thing is added here in the, where is that?
So basically, what I thought about the transitive closures, like we will write all the edges like A, B, C, D, E, and like in horizontal ABCD and vertical. And if there is an edge between A to A, we will assign it 1. If a edge between A to B, we will assign 1. If it's not,
Yes.
we will assign 0. Just I thought the transitive closure is to just find there is a path between these edges. And there is any significance more than this.
So significance is in the Floyd-Warshall algorithm.
That I know, sir.
Sir, I think
Further.
transitive closure is used to find transitive relation. If A and B is related and B and C is related, then B, A and C is also related.
So that is one. That is what we are doing. That is what. If the related means if there is an edge is happening, then we are adding.
Right.
Yes,
Right, so
we
I
define
think what
relation.
is right, what he has told is right. I think if there is between A to B, there is edge, there need not to be edge between B to A. Like it's the marking, na? There is a marking of in transitive closure, like uh, arrow mark. There
I
is such
think
kind of
I'm just
concept
missing
in the
one thing.
transitive.
Just a minute. I think I'm just missing. If just a minute. Let me. If two wet length, if there is one, no, there is a length up to of that path, then we'll connect, or for any
Arrow
path.
marking. There is an arrow between edges. If there is, yeah.
Path of length 2 is there. Okay, just a minute. Let me see once the definition. No. So there is a path. If there is a path, so then we'll. So there is no of length 2. If there is a path, then we'll connect. So I'm correct. There is no error in my what I'm doing. So if there is a path, then we'll connect that
So
edge.
we are connected. Yeah.
We'll connect an edge. We'll add a edge which will connect two vertices.
Right.
Okay, so
plate
use is generally use. So what is here? Okay, so what is happening here? If you are not understanding, so what is that here? Okay, so where is that? Okay, so this transitive closure, no, we can easily compute with the matrix multiplication. Very easily we can compute with the matrix multiplication. And how we can do? So first thing you have to understand what is the matrix, and then matrix multiplication. Then how many times we have to do the matrix multiplication, that is going to be transitive closure. So let me give an example here. We can exactly get this one. Okay, so we have A, B, C and D. Okay, so previously we have this graph, no? So what is going to be the matrix of this graph? Adjacency matrix. This is A, B, C, D. Here is E. And here is A, B, C, D, E. Okay. So let's first A and D, we have a edge A and D. So this is 1, and this is undirected graph. Okay, this is undirected graph. There is no issue. A and D and A and B we have, and okay, that's all. And B and C we have. Okay, that's all. And C and D we have C and D. So this is 1. And rest all we will fit with 0. You can easily check that this is going to be your adjacency matrix. and D is connected A and D. So D is connected A and E, and rest all will be filled with 0. And E is only connected with the D. So, sorry, E is only connected with D. So see that this is diagonal is going to be 0, 0, 0, and same thing will come here. Okay, this is one. I think this is correct. If
Sir,
the
C is connected to D and B. We have not considered that.
C is connected to D and B. Here is that's the error.
Yeah. And D is connected to C and E.
D is connected to C. D is connected to C and A. Okay.
E.
A also. So A.
Yeah. A, E.
C and E. Yeah, this is correct. Yes. So yeah, now it is fine. Okay. This is now fine. So this is the adjacency matrix. So either if you want, we can write like this. You have to at least remember the order. It will be order with the order is going to be same. A, B, C, D, E for horizontal and vertical both. So this is 0, 1, 0, 1, 0, and then 1, 0, 1, 0, 1, and then 0, 0, 0, 1, 0. So this
Sir,
is the
B is
matrix.
connected to A as well.
B is connected to A, and yeah, here is 1 is going to be. Yes. So it is a kind of symmetry will happen. Whatever the thing is will come here. Yeah, it is actually coming the same. Yeah, this one. Symmetricity will happen. Yeah, now it is symmetric. Now, what is the matrix multiplication is that if you multiply with the same matrix 0, 1, 0, 1, 0. Okay. Then 1, 0, 1, 0, 0. Then 0, 1, 0, 1, 0. Then 1, 0, 1, 0, 1. And next is 0, 0, 0, 1, 0. Okay. Now, how we will do the matrix multiplication here? It is going to be okay. So it is going to be now. You will take this row and we will multiply with this column. With this column means this one, the first column. You will take the first row, this row. Okay. You will multiply. You will take the first row. Let me write here 0. You will take this row and multiply with this column. Okay. So what you can do now? Let's check that. So how it will be multiplication? 0 will be multiplied with this. 1 will be multiplied with this. 0 is multiplied with this. Please all of you mute yourself. So the whatever the order is there now, in the same order multiplication will happen. Okay. So okay, so 0 into 0, and then 1 into 1 is there. This one is multiplied with this one. 0 is multiplied with this 0 plus 0 into 0. Then this one is multiplied with this one, 1 plus 1 after this plus, and then 0 and multiplied 0. So this is the first entry. And what is the property? If you do 0 times 0, you will get 0. 1 times 0, you will get 0. 0 times 1, you will get 0. 1 times 1, what you will get here? 1 only. And addition, how the addition is 0 plus 0 is 0. 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 1. Using these two things, we'll do multiplication. So you just need to, you can remember with the, how you can remember? See, anywhere is 0 time 1 is there, then it is everywhere is 0. Only 1 is there, then it is 1. And in addition, everywhere is 1. If there is 1, then 1 is there. The 1 is then 1. 1 is there, 1. Only the 0 plus 0 is there, 0. By this way, you can remember. So this is going to be 0, this is 1, this is 0, this is 1, and this is 0. And there is a plus thing is there. So 1 by 1, if you add, this is going to be 1. And if you add this, this is going to be 1. And 1 plus 1 is going to be 1. And then add this 0, this is going to be finally 1. So finally, this entry is going to be 1. Similarly, you can do multiplication. Okay. So by this way, you will do multiplication. And how many times you will do multiplication here to reach the transitive closure?
Five times.
Why 5 times?
There are 5 rows and columns, so
So 5 times you will do or 4 times?
5 times.
5 times. Number of vertices, if how many vertices are there, that many times you will do multiplication. That will give the transitive closure.
yes.
And then after we'll stop. If it is a 5 vertices is there, then 5 times we'll do. If it is 6 vertices there, then 6 times we will do. Or one lesser than that.
No, sorry. Matrix is 5 by 5. Then the final result is also 5 by 5.
So multiplication will be 5 times, right? Okay. So how many vertices are there? That time you have to do matrix multiplication. If there is no if there is no, so there is no need to go next time, means you don't need to do multiplication 6 times, just need to do 5 times if 5 vertices are there. So it will take time for here. I just choose the longer one. Otherwise, if you do the star, if you do the multiplication 5 times, you will reach to here with whatever this matrix have, whatever this graph have adjacency matrix, you will get exactly, if you do 5 times multiplication with the same, you will get this one. Okay. Now let's move to the shortest path.
Hello.
Mhm.
Yes, sir. I have a doubt from previous week.
Okay. What is your doubt?
Oh, it was about detecting loop using DFS. Yeah, I didn't quite get it. Like, how was it working? Can you please
Loop.
explain that? Yes, detecting a loop in a graph.
So if loop is, if you count, loop means here is simply, you just given a weight. Okay, suppose I'm making a weight here -5, 1, 2, and 3. Okay, here itself. So if you weight this, count the weight here is, let's say 2. Okay, so this is a cycle, right? This is a cycle in the graph. And if you count the weight here, even let's say this is 8. This is 8 and this is 3. Now if you see that the weight of this cycle is how much? What is the weight of this cycle?
-2, I guess.
No, this is 5, 6. Yeah, -2 is there. The weight of this cycle is -2.
Yes.
Okay. And you are finding the shortest part. So what is that weight is? In that case, if you are getting the weight is negative, then it will form a loop. Your weight should not be negative. That's the meaning here, the loop. Cyclic.
Okay.
If your weight is negative in a cycle, weight of a cycle, not even weight of a graph, I'm saying weight of a cycle is becoming negative, then it is a trouble.
Okay.
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 Now
Yes, sir.
sort.
Sir,
Yes.
hello. Sir, I think we don't need to do multiplication of matrix in transitive closure.
Sorry. Transitive closure.
In transitive closure, you know, we don't need to multiply two matrices, I think.
Yeah, if it is a graph, no, then there is no need to multiply. If it is there is no graph, only the adjacency matrix is given, then you have to do the matrix multiply.
Sir, if you multiply these two matrices, like you write over, then we get 2.
So we will find,
Or
we will find
A2
so if you 2 times, so what is that happening? If you are multiplying, multiplying this vertex, sorry, this adjacency matrix. So what is happening here? Suppose this is the adjacency matrix. I am doing a square, which is I am 2 times I am multiplying. So if you whatever you will get here, adjacency matrix, no, whatever the adjacency matrix you will get here, right? So what is happening here? If you draw the graph of this adjacency matrix, what is the graph you will get? You will get a graph. So what is happening here? Whatever the graph you will get, no, that graph is actually you will connecting that edge which have the length of, you are connecting two vertices which have the length is 2. Sorry, length is, or length of a path is 2. So what is the meaning of length of a path is 2 means? Suppose I am just, we have this one, right? This edge is there. So what is the path of this one is? Length of this path is 2, right? Length of one length and then another length 2. So if you 2 times do multiplication, no, so sorry.
So what I understand by lecture,
Yes,
sir,
yes.
I think if we talk about a square,
yes,
then we need to reach that vertex by 2 edges. Then we note it as 1. Like if we talk about A and B,
yeah,
then we need to travel by 2 edges, like AD and DE. Then we write 1 for
yes,
AE.
yes.
I think this is a transitive closure. If I'm wrong, then
So what is the meaning of, doing the multiplication means you are finding a edge between those two vertices which have the length is 2. Length of a path is 2. What is the meaning of this one is? The meaning of this one is, and by example, this example we can understand that between these two, this vertex and this vertex, this path is length of 2. This path is of length 2. So if you do the multiplication, you will see, and whatever the adjacency matrix you will get, if you form that graph, you will see that in that graph these two will be connected, because this is the meaning. If you are doing the square, no, that means you are getting a adjacency matrix of that graph, that updated graph which have the, you will connect those two vertices which have the length 2, means those two vertices you will connect, because those two vertices you will connect, which you will see that have path is 2, you will connect those two vertices. Like if you'll say you will whatever the updated graph adjacency matrix you will get here, you will not see, okay, here is already 2, 1, 1, 2, 3. So 3 is path is 3. Yeah. So you will not see an edge between this one. You will not see in this, if you form this adjacency matrix, you form the graph, you will not see the edge this one, but you will see the edge this one. Why? The reason is, between these two vertices, if you count the path, the length of the path is 1, 2, and 3. The length of this path is 3. But if you are doing the square of these two, and if you form that graph, you will see there is no edge. The reason is this path is 3, but this edge will be added. Means if you draw the graph of this adjacency matrix, you will see there is an edge. The same graph you will get, but there is an edge between these two.
We get 2, then we write it as 1. Like multiply these two matrices.
Sorry.
If we get 2,
then
we write it as 1. Like if we multiply these two matrices, like first column to first row, then we get 2.
So 1 plus 1 is not 2. 1 plus 1 is 1 only. This is the binary addition is there. This is the binary addition. Okay. So 1 plus 1 is the meaning of is going. So by this definition, you will do matrix multiplication. Okay. By this definition, you will do matrix multiplication. Not by your own way that 1 plus 1 is going to be 2. 1 plus 1 in the binary addition, 1 plus 1 is going to be 1. So by these two operation, you will do the matrix multiplication. It is not a kind of usual way you will do as you used to do the matrix multiplication with simply as in the 12th. I don't know in the 12th is there or more than that. Same again in BSc, I don't know. But here is some constraints is there. With this definition, you have to add 2 entries or multiply any 2 entries by this property, that if you have 0 times 0 is going to be 0, only the 1 time 1 is going to be 1, otherwise every time we'll get the 0. Now let's find the shortest path is there. So shortest path is, there is one the Dijkstra algorithm, and there is one Warshel algorithm. There are 2 ways. There are 2 algorithms. There is one algorithm is Dijkstra algorithm, which is actually not allowed for the negative weight edge. But now the next algorithm, updated algorithm is, that algorithm is called Warshel algorithm, I think. Yes. And the Floyd Warshel algorithm is updated all vertex to all other vertex. But Warshel algorithm is, we'll see now what is the Warshel algorithm. So what is the Dijkstra algorithm? So for example, let me take the same. So this is a graph we have. Okay. Now there are 2 ways to, suppose you want to find the shortest path between this vertex to the vertex T. What is going to be the shortest path between these 2 vertex? By which way we will go so that the minimum weight we will get. That is the meaning of the shortest path. So there are 2 ways. The one is the Dijkstra algorithm and another one is the Warshel algorithm. So Dijkstra algorithm is not allowing any negative weight edge. So like here this edge have the negative weight. So in the Dijkstra algorithm it is not allowing, and we will not apply the Dijkstra algorithm. We will do the for Warshel algorithm. So here, if you suppose this is exactly 2, this is exactly 4, this is exactly 6. So now there is no negative weight edge. Now here we can do the Warshel algorithm. Now we want to find the shortest path between A to D. So by which way we will go so that we will find a path which have the minimum weight. So what is the Dijkstra algorithm? So it is a kind of thinking about the fire, that you have at this place suddenly you got fired, and the fire will start moving in these two ways.
Sir,
Yes.
the diagonal is like once we change the weight of the any edge, we cannot
Hello,
change
hello
it again.
guys.
Like once we
You
change
are
it,
interrupting the.
if we found it lesser than that, also we cannot change it because we have already changed it.
No, here I change because of the negative weight, and I'm not going to the negative weight.
I'm asking like diagonal algorithm is like it will not work for negative cycle, and it's like once we change the like there is an edge between A to B, we will there will be the weight of the B is infinite, so we will put A to B as 1. But once we put A to B as 1, we cannot change the B value because we have already done it like 1, right?
Yes, that is Warshel algorithm. Yes, it is in the Warshel algorithm. Yes.
So, as I remember, there was like in Dijkstra algorithm is also same, like we cannot change now. Once we change infinite to 1 or anything, any value, we cannot touch it again now.
Yes.
Yeah. Yeah, I got confused about.
Okay, so you are saying in starting, so here, yeah, okay, so exactly you are moving with the infinite thing. So yeah, so at the fire time, in the starting time, every age is have the infinite weight.
Yeah.
What is the meaning of infinite weight? Means you got fired, like this place is got fired. Okay, so
Right.
from here we don't know exactly what time will take, but that's why that's why the infinite sign is generally given. Okay,
Right.
but we know that here, so the fire will start moving with the not moving with the minimum age.
Right.
Start will with that age, means the fire will start moving in this direction and in this direction both, and
Right.
within 1 minute, yeah, after 1 minute this station will be fired. But if a fire is moving here, so it will reach to half, and from this place the fire will start moving this way, this way, and this way, and within 2 minutes, or after just 2 minutes, this station will be fired. But after
Right.
this will take 2 minutes, and this place will take 1 minute ahead more than that. So before 2 minutes, this place will be fired. Okay, and how much time it will take to reach this place, and this much time will be taken from fire here to here,
Right.
right?
If there was any negative value, we cannot use the stack algorithm because it will not work.
Sorry.
If there was any negative value over here,
Yes, then
negative
it will not work. Yes.
work, because once we have changed the infinite to any value, we cannot change it again.
Yes. Now it is a kind of, now we reaches very soon to here D, and I said I am finding the weight of, or a shortest path from A to D. So by this way, so this Dijkstra algorithm says it will move ahead, and actually it will reach to all vertices here. The fire will reach to all vertices. So within 2 minutes, within 1 minute, it will reaches to this one, but fire will move this way, and this way. So within 1 minute or after just a minute, the fire will reach here. And from here, the fire will start moving by this way, and it will take 3 minutes to reach. And here, it will reach to 1, 2, 3, 4. At 4, it is reaches. And here, by this way, it will reaches to 2.
Sir, this Dijkstra algorithm will not work for negative weight cycle, or it will not work for negative value only.
It will not work even for the negative weight. The weight should be only positive.
Okay.
And negative weight cycle is not even you can think with the any algorithm.
Flow reversal, sir?
What is meant by negative weight cycle?
Negative weight cycle means a cycle. There will be a cycle which have the negative weight.
Means overall, when we add all the paths.
All the paths, not even all the paths.
Multiple
that cycle, like suppose this is a cycle, no? This one is a cycle. This is a cycle. This is a cycle is happening here. And if you count the weight here, what is the weight of this cycle only? What is the weight of this cycle?
0.
No, it is 3, no? This 3 and 2, 5, and this minus 4, this is 1.
1. Okay.
Weight of this cycle is 1. So it is not negative. So this is true for, flood, even Kruskal, any other algorithm to find the shortest path. Okay. But by suppose I am saying, suppose this is 6 here. In place of 4, minus 6 is there. Now if you count the weight, this is going to be minus 1. Now we are in trouble, and in that case, we are not going to work for even, Warshel algorithm or Kruskal. Kruskal is even not allowing the negative weight also.
Okay.
So this is the meaning of negative weight cycle. Okay, so we are discussing.
There is one formula for like this. There is like in like V2 is there, or I don't remember. It's like we have to place it, I think, infinite, and we have to place, I think, A to B values.
That is Warshel algorithm. That is what Warshel algorithm. I am discussing now the the extra algorithm, the Floyd Warshel. So not Floyd. Warshel algorithm is exactly you have to to write in matrix form, and you have to proceed with weighted with weight in the sense of we'll start updating. In starting, it is going to be infinite lattices. Then the update you have to do each time. So here is not we are doing with the Kruskal algorithm. Sorry, yes, not Kruskal. Yeah, Dijkstra algorithm. So Dijkstra does not allowing any negative weight edge. Now that's why I'm saying how with an example of fire I'm explaining. So let me explain again. So what is here is happening? Here is, suppose this is there is no negative. Okay. Now from here, this station got fire. So it will take 1 minute to reach here, and 1 minute to hop off here. And again, fire will start moving in these 3 direction. And within 2 minutes, it will reach here, but it will take 2 minutes. So here it will take 1 minute and then 1 minute. So from here, fire will start moving this way, and this way. But within 1 minute, this one, and then this one, it will reaches to the place where we want to find the shortest path. But our work is not done. We have to complete our work with all vertices. Now it will start moving this direction, this direction, this direction. So after 1 minute, it will be here.
Sir? Like what I mentioned was like the addition thing. Like there is a path between A to B, right? So here we will do like this. This is the value of B is infinite, and the A value is like also A value is like 0. Means starting there is no in degree, na? So it will be 0. So 0 plus 1 is less than infinity. So we will be inserting the value of b as 1, and the value of c is infinite. So the b plus 2 is 3, and 3 is less than infinity. We will be inserting the value c has 3.
Yes, yes.
And and like if and same for this, but like see b2, the value of b is 1, and the path b to d is 4, and it will be like 5, but c to d it will be like 1 3 and 6, and the 6 is 5 is less than 6, so we will be keeping the value 5.
Yeah, that is whatever you are saying, that is in the Warcel algorithm. That is exactly in the Warcel algorithm. If it is lesser than, we will keep that, otherwise we will update. So, but here, what is the
So here what we will be doing, sir, like there is a path from B to D also, and there is a path from C to D also, and there is a path from F to D also, and there is a path from E to D also. Or which value you will be considering?
So we are considering that way. That is a fire, exactly as fire method. That timing and fire method. This is 4,
Okay.
this is 2, this is 6. Suppose
Right.
this station got fired. So in these
Right.
two direction, fire will move, and after 1 minute, this station got fired. And on this part, fire after 1 minute is here. But next, after means here after 2 minutes, this station will fire, and this in this way here is fire start moving in this two direction, and after just a minute here it is take 2 minutes. So here after 1 minute it will be here, half of that, half of it. And here is after 1 minute it will be here, and after it will be here 1 minute. So these are the places is there. Now in the next minute it will start moving this and this three direction. So after just a minute the fire will be here. Okay, and now in the next 2 minutes the fire here will be here, and here everywhere is 2 minute is there. There is 2 minute, 2 minute. Now next 3 minute is there here, in here is in the next 3 minute, but here is what is happening. It is already 2 and 3 is there. Then it will move this side, back is this, not back, this side, and this side, this side is there. So what is that? Exactly the way you will think, catching the fire at the station. And by this way, if you see if I will ask what is going to be the weight of the minimum path between A and D, then by this way, by this way you got, and here it will have the much weight. But if you go with this and this, then it have weight 3. So then shortest path is going to be in the terms of weight is going to be this and this. Okay. Exactly on thinking on the fire, catching fire, and how much time is already written in the weight form. Okay. And then you have to think that how the fire is moving, how
So
much
on
time.
any given graph, we have to find the shortest method through whatever you just told now.
Whatever by this way you can.
Manually.
This is the Dijkstra algorithm. Yeah, this is the exactly Dijkstra algorithm. Warcel algorithm is finding the matrix form, which we will see in the next session, I think, with doing
Sir,
the
if
solving.
the number of matrices are high or vertices are high, right? This becomes very complex, right?
Yeah, in that case, it will become complex. So then you can do the Warcel algorithm. In that case, you can do the Warshel algorithm, updating in the matrix. We'll see the Warshel algorithm tomorrow. We will see what is the Warshel algorithm. And Floyd-Warshel will try to skip. So for that, I'm suggesting you please watch to come tomorrow in the next session. Please watch at least one of this tutorial. Open session and solve with us any one of them or both. If you will be a watch, then everything will be much clear. We'll discuss it.
One question I had on the cycle. One question I had on the cycle. Sir, if there are two vertices A and B, and A goes to B and B goes to A, so does this form a cycle?
No. So in that case, we are not thinking. No, again, you are asking the same. So that is we are not going to think. Those things we are not going to think.
Means?
So that.
No, I'm asking whether it's a cycle.
You are saying like this.
Yeah.
Right. So in this case, we are at least for this course, don't think like this of kind of cycle.
Sir,
Yes.
I want to share my screen. I have a question on this, sir.
Okay, so you can take the screenshot and post in chat.
Sir,
Okay, so
if you allow me to share the screen,
no,
it's in question.
I don't think I have access to allow you sharing the screen.
You cannot open the Bible. So sorry. I think I can share. So
no, I don't have.
Yeah. Sir. I will share it, sir.
Yeah, please to post in chat. Yeah. Next is somebody is asking some week 9 doubt. Okay, what is the doubt?
Sir, I have a doubt in week 9.4 activity.
9.4. Okay.
Sir, it's showing that host is disabled to
First
attend the screen.
Yes. Which question?
Second question.
What is the doubt?
Can you explain the concept? I will solve that question. Actually, I studied the entire theory about the Riemann sums, and I didn't understand how to solve the examples like theta, xi, how to calculate that entire equation.
Okay, so actually it will take time to again you explain. Did you were present which when I were discussing about the partition?
No, sir.
You were not there, no? So before to discussing, I will again suggest you if you watch that very slowly. I took time and 1 hour to explain then what is the partition and how you will do. I will find how you will find the
Actually,
answer.
there is only one session.
Yeah, only one session is enough. Only one session is already there, and in on the single session I have discussed everything, even the partition, what is the partition, what is the norm.
Okay.
Otherwise, I will again it will take time to explain you, but it is in here in this session. This the days is already you can see on the 25, and if you see that actually I took time here and I slowly explain what is the partition. Okay, 1 hour I took how what is the partition, how you will find the norm, even with the example I have discussed what is the regular, what is the norm. Regular norm means one norm, what is the norm definition even, and how you will find the norm of a partition.
Okay, I will watch that entire video. But can
Yeah,
you
you
solve
can watch very
questions for
slowly. Then
9
I have
and
whatever
10?
that question you are saying, I have discussed in that also to
No
finding the
problem.
norm.
But I have a doubt in other two questions. So
Okay, what is the doubt?
9th and 10th question.
Yeah,
Same
in this
activity. Same activity.
9, 10. Okay. This is the finding of mid-Riemann sum, right? This is, so do you know what is the mid-Riemann sum?
Yes.
So then it is fine. No, here it is, you have a function. So this example we have did also there, and this is exactly finding what is the mid-Riemann sum. You just need to divide your interval in how many
Can you
in
solve that question for me?
sorry.
Can you solve question?
Yeah, actually it will take time. It will take time. It will take time to solve that. I have to, it will take time. So
Okay.
I should to do earlier it. So first thing what you can do, in this problem nothing is there. You just need to find the midpoint and do the Riemann sum. So again I will suggest you, if you watch that with this example even I did with the Riemann sum I did. That's the same
Okay.
example I have completed there.
Okay.
Okay.
Sir,
Left Riemann sum, right
it's a
Riemann sum, mid
little
Riemann
query.
sum.
How
Sorry.
to choose that theta xi value?
That theta x, yeah, sorry, x star.
Yes, x star.
This the xi star, right? How to choose
Yes.
this one?
Yes.
So here already definition is given, no? What is this definition? What is the star meaning? That is here is the meaning of left Riemann sum you are finding, and this sorry right Riemann sum, and this one says the left Riemann sum you are finding. This is also I have discussed. So again I will, even this whole question I have discussed there in that session. Could you
Okay.
please watch that? Then it
Yes.
will be very easy.
Okay.
Otherwise, it will again take time for me to 1 hour to discuss again, because I have to tell you the partition. I have to tell you the norm of the partition. Then what is the left Riemann sum, right Riemann sum, mid Riemann sum, and with an example I have to discuss.
Okay. I will watch that video.
Yes. Yes. Yes.
Thank you.
Sir,
Yes.
you have disabled to show the screen. If you can, there is a, if you click on A1, it will,
I don't know. Just a minute. Okay.
you can find it, I think, on our setting.
Chatting name allowed to multi. No, there is no host only can give can allow. There is chat asked to start video. Pin rename allowed to ask, no rename. There is no sharing thing. Remove and remote. Sorry, report. Yeah, there is no. I think host can do, but I cannot do this one. I cannot allow
Okay,
it
okay.
to. There is
Tomorrow
no
I'll share.
option. Oh, so you can
Because
no,
it
you
was
can. So what is the question? Can you tell me what is the question?
like it's a matrix question, like it is
Hmm.
like let's a square is equal to into a. What will be the value of 2 alpha plus beta? And there are two matrices. It's like picture.
So is this from
Is
activity?
this from activity? It's from last year question, but if you have, I think I can provide you the access. Just a second, sir. Last year
Sorry, sir.
question paper, I will share the. I will paste it.
Yes.
No, you can cut and paste it, no, in the chat.
No, I
Chinmay.
think. How can I paste the question paper? How come?
No. You take a snapshot of it and paste it here
Okay,
in the
okay,
chat,
okay.
like what I have pasted.
Okay, just a second.
Meanwhile, sir, can we look into that particular question? If we
Okay.
perform BFS in a directed graph, how many times do we check whether a vertex is visited? So this I'm not able to understand.
If we perform BFS in a directed graph, okay, how many times do we check whether a vertex? Please, all of you mute this. Okay. Some noise. How many times do we check whether a vertex V is visited? In degree, out degree 2, 1. How many times we will check that?
So I have a question.
I think I think it's only once we visit, right, sir, in the BFS.
So it is just for visited or explore. How many times do we check whether a vertex V is visited? How many times do we check whether a vertex V is visited? How many times
degree. In
do we
degree.
check whether in degree is fine? That's why I'm yeah, that is one. That is one thing. Yeah, that is one. In degrees, number of in degrees actually will tell you how many times you will actually what is the meaning of here. That in BFS, okay, if you have a BFS, this one. So this is a graph you have A, B, C, D. Okay, and this is your graph, and this is a directed graph, right?
Yes, directed graph.
Directed graph. So suppose this is one and this is one. There are two in degrees, and suppose this is one.
The BFS we will check one time, na? First in, first out. It's a last in.
So let's see that what is happening here. So we have vertex C. Now I started the BFS from A. So BFS from A means this. So what is going to be this one? So visited the vertex B once here and visited the vertex D once here. Okay. And also visited the vertex C.
Yes.
Once here. Now here is B is here, C is here, D. Now these are at the same level, 1, 1, 1. That's the meaning here. At the same level these are. Now we start exploring B. Now once I started exploring V, then I can visit, see that, because there is a vertex outgoing which is here and incoming for C. So it is asking for V visited. So for here is the in degree is given for V and out degree of given for V, but here is what is happening in degree for C is happening. So this is not going to be how many visited. So number of incoming edges. So how many times I visited by this way and by this way, right? By this vertex A I visited here, and from B now I visited again C. Correct. So two time I visited the vertex. See, so number of in degree time I am visiting the vertex V. Okay, so here it is going to be in number of in degree. Not even fixed number 1, 2, not even fixed number, but yeah, number of visiting time is in degree. But here it is a MCQ, you know. So, but still, it is a number of in degrees there, and not only once.
Even if it is at level 1, even if it is at level 1.
Here level 1 to any level. Here is what is the level of this one? Here is already visited, no? No, it is just a visiting. I am visiting this one. So once we will form the queue, right? In form Q from A, I visited B, from I visited B, C and D. Now once I started exploring, okay, now once I started exploring, so now I started exploring B. So from B I can visit C. Okay. Okay, that's all. I can visit C, and I already visited A and already visited C also. So how many times it is happening? It is happening. So these two option is going to be true. One is already one. Once I am how many times already A is visited, but number of in degrees also time are visiting. I'm not sure about it. How many times it is happening? Is this activity problem? Is that from older period? I don't know.
It's an activity problem.
Which activity is this? What is the answer for this one?
It's in degree.
in degree, right? So yeah, from B also we are visiting. A from A already visited. Explore is ending, like exploring. Visiting is like 2 time, 3 time, but exploring is that once we are exploring in BFS. In degree, yeah. In
Visiting
degree
and
is fine.
exploring is, I think, same only, right, sir?
No, visiting is different, exploring is different, no? Till now I didn't explore C, but visited 2 times. From A also, from B also, right? From A also I visited, I able to see C. From B also I able to see. But till now I didn't explore C, right? I explore first B. Now time to explore C. So once you explore C, D will be here now. Okay. And now from C, what are the vertex I can visit? Which is already explored. A is already explored. B is already explored. So only now turn to D. There is no visiting vertex for C. Now I will go to the level with the same level which have D here. Now I will start exploring D now. And again from D already A is explored. So nothing is done and Q is now empty. So this is the stopping thing. Yeah, so visiting is here, number of in degree is happening, and exploration is one. Exploring once, but visiting is number of in degrees.
Sir, is it possible that for all the activity questions, no, we can get a PDF without the answers? Because I tell you what happens is when we are solving this, right, sir? Okay, there is a high tendency to check the answer first.
Yes.
Okay, so as like what you are doing in the graded assignments, right? So when we are doing graded assignments, we go with the flow and we will realize whether our approach was right or not only after the solutions are given later.
Yes.
Okay, that is much more beneficial to learn than this activity questions, because as soon as we do some questions, no, we might sometimes not be serious, or we might miss something, or we might not. And as soon as we see the answer, no, we tend to modify our approach, as like what we are doing now for in degree.
So okay, so one thing we can do even easily, no, okay, either we can provide or all of you yourself, you can also you can take the screenshot of and paste in the notepad and form that in a PDF format. That's all. By this way, you can easily do. Because this time we don't have the
No,
in the one.
it is easier for you all to do. You will be doing only once. But if 1,000 people are working on this, 1,000 PDF they have to create, right?
That's one part. Yeah, that's one part. Okay, so maybe I will tell to TS. Okay, so I need to tell to TS that they will take a screenshot of each activity and form a PDF, and maybe I will update in one of the summary, live and with the summary session even. Yeah, we can do
Yes.
that.
Question my question.
Sorry. Yeah. Okay. Just a minute. So let me tell to TS also now itself.
Sir,
Mm-hmm.
sir, TS also already provided these questions in Jamboard. They solve questions, activity question, and they share the Jamboard link in chat box.
Sorry. Just a minute. Sorry. What are you saying?
Sir, students ask their doubts to TS.
Mhm.
They solve in activity questions. They solve in Jamboard, and they share the link at last in the session in chat box.
Okay. They usually
That is okay,
sharing.
Trisha.
They are.
They are sharing the
Okay.
answers. Means they'll solve. That is okay. But what I was asking, sir, was the PDF of the activity questions. If you are
Whatever
referring to
they
that,
are
then it's okay.
solving, I'm okay. So that is not always like they can do. Okay, so Jamboard link can be easily no in Jamboard you cannot. You cannot share the link of PDF, right? In Jamboard, you can it will, if it will be erased, then erased. Is there any option to share that? No, I don't think so.
No, Jamboard, like sometimes it is shared, sir, which it goes to a Google Drive, and from there we can take the Jamboard file if the instructor shares. Okay, but that
Okay.
Jamboard file will be a solution which is done like what you are doing now. It's a plain PDF without any activity question number or whatever. Okay, without the question and all. So that anyway we will note down when we are attending, right? This is for this particular question and so on.
Yeah, yes.
But the it will be grateful if you give us the PDFs of all the activity
Yeah,
questions.
that would be, I am just wrote to, they will collect.
It's
Okay,
the same. Yeah, it's the same program that you have to run for as like you run for practice questions, right?
Yeah, it will be now available, so don't worry. I will just already given that, and they will collect all. Okay. And regarding the Jamboard, I'm not sure about it. That is TA is only, you can come and ask. That's why we are not recording, even not even on YouTube. It is your like one mentoring thing. Already it is going on. But it is, if you have doubt, just come to TAs and they will resolve your doubt. That's all. That's why it is not sharing, or it is not keeping, or always keep the videos or PDFs and then back to you. If you have again doubt, try yourself, not able to reach that or not able to solve, just come back any one of the session and ask again. Okay. Okay, let me see that somebody has given. Okay, let A square. What is the value of 2A plus beta? Okay, so you are saying with what is, sorry, 2 alpha plus beta. Beta is there. This is A square. So you have to multiply first.
Sir, for beta multiply M into K.
Okay. So here is 2
for alpha multiply I and J.
So first you have to, in this, you have to find A square anyhow. So you have to find the A square, whatever you will find. And then whatever the alpha, if it is 0, then 2 times 0 is going to be, if we are doing the binary operation, then how it could be 2 times 0. And if it is 1, then 2 times 1. What is going to be answer here then? 2. No, it is not correct. No, how it could be in the binary operation?
Sir, its answer is 1. 2 alpha plus beta is equals to 1. Because alpha is equals to 0 when we multiply I into J.
No, so how if it is a binary operation 2 times 0, then how it is defined? No, that our definition is only for 0 and 1. I'm not sure.
I think it's simply multiplication of matrix.
So no, but our operation is only binary multiplication, 1 times 0, 0 times 1, and then 1 cross 1. If 0 times 0 means it is a normal multiplication. It should not be like this is not a binary multiplication. This is normal multiplication. In that case, it is, yeah, if it is 2 times 0, then
Yes,
beta
sir.
is 1, then it is going to be 1. But this is a normal multiplication then. Here should be in the bracket, should be written there, it is a normal multiplication. Then it is a correct. No, otherwise it is not correct.
Sir, in lecture, sir, also do normal multiplication, not binary.
No, it is not normal. In lecture, it is not normal multiplication. I am sure.
Sir, in multiplication of matrix, there is
In
normal.
multiplication of matrix it is.
I think it's a question of normal multiplication, just multiplication of two matrix, not binary multiplication.
So in that case, it is A cross A is A square.
Same question also.
Some portion is missing of this problem. Otherwise, it will be solely instructed in some part that it is a normal multiplication or it is. I think it is a part of some question, right?
No, sir. It's a separate question only.
It
There
is
is
a
no any
separate
part.
question.
Yeah.
So if it
Before
is a
this question
normal
is like
multiplication, then it is true. Then it is going to be 2 times 0 is 0 plus 1 it is 1. But if it is in this mode, then it is not defined. You have to define first. 2 times 0. What is 2 times 0? Because it is whatever we know, it is binary multiplication is here only. 2 times 0 is no, there is no mean. But if it is in normal, then it is true. In the
Same
normal.
question also in activity. I don't remember number of activity. But
sir, I have
if it
pasted
is
that
in the
Google
particular
Drive.
activity, then it is. So I think it is of normal multiplication. I think not. It is actually the more normal multiplication. Then it is true. And it is
Sir,
happening.
I have pasted the Google Drive. If you check, there is any relation between before and after questions.
Sorry. Where is that?
I have pasted in chat box. Google Drive, IT Foundation, Diploma, Enter.
In this chat, no? This whatever we are in the Zoom chat.
Yeah. Zoom chat.
So your is already I'm able to see. Now next is Siva have given Siva, yes.
I'm asking like if you needed like
okay.
You asked not relation.
Oh.
There is any before and
Okay.
you check it,
Okay.
you find it.
No, so it is a separate question. I think you are saying.
Yeah, if you scroll down, just scroll down.
So which page number directly you can tell?
Just a thing. This page number 39.
Question number 77. Type essay. It is normal. Enter your nearest integer. No, very case.
What I was thinking like
yeah, it is a normal. Then it is a normal multiplication. Then yes,
sir. Just I don't get the logic. I thought it in like a float washer algorithm, like I to j is infinite, but in before a, it's I to j value is 0, and k to m value is beta, and k to m value in a is 0. So I thought like it's 2 into 0 plus 0. It should be like value, but my logic also got wrong. I also don't get it one.
No, so it is normal multiplication. No information is given. Then normal multiplication we can assume. Otherwise, there is no meaning of 2 times 0 in the binary multiplication. So it is a normal multiplication is that.
So normal multiplication is like.
So normal multiplication is going to be, now you can multiply the same with the 0 time. This is yeah, it is. If you do the normal multiplication means take this row and this, if you will take this row and multiply the same column, so everything everywhere is going to be 0 here. This alpha is going to be 0 value.
Right.
Sir, but beta is also 0, no?
So if you want to find the beta, that means you have to take this row and multiply with this column.
How beta is 0? We multiply m and k now.
So if you multiply this, if you have to take this beta, if you want to find beta, then you have to take k and then multiply with m. Then this is going to k. So this is
Then
0.
1 into
This is
1 into 1 into 1 and no. How beta is equals to 0?
So here is okay. So just a minute. So this is going to be.
No, we have to multiply like the
I
first.
row first row and first column means I multiply by I, column I and row I.
So yeah, it is happening 0. No, beta is we are
Then
getting.
how come we multiply k with m?
Yeah, it is actually coming 0. Right? This is actually coming 0. So 0 times 1, 0 times 1. This 0 is 0 here. This 1 is going to be. So no, this 1 is here, and 1 into 1 is 1. Yes. And all will be added, no? Okay, so 0 times 0, 0 plus, so 1 time 1 is 1, and then 0, 0, 0 plus 1 plus 0. It is coming 1. Okay, sorry. So beta is coming 1.
Like 2 into 0 plus 1. According
No,
to the question.
yeah, 2 into 0 plus 1.
Yeah. Bit tricky.
It is not tricky. It is defining a normal multiplication. Yeah, tricking, if it is clearly mentioned that it is a normal multiplication, then everything will be obvious. Otherwise, yeah, many people will think with
come over. If you can come with this like questions before few questions, it will be better. Because
Okay.
I had access to question paper. I found it few, but you will be having access to many questions like this.
For that such problem, we have already doing a session with older key questions. So we have already we'll used to do. Okay, that's all for today.
Sir, could you please solve for beta?
For beta means here what is happening here? 0 times 1 plus 0 times 1 plus 0 times 0 plus 1 times 1 plus 0 times 0. All will be added, right? What is you are getting? 0 times 1 plus 0 times 1 plus what? 0 times 0 plus 1 times 1 plus 0 times 0 you are getting. So this is 0, this is 0, this is 0, but this is 1 and this is 0. So 0 plus 0 plus 0 plus 1 plus 0, which is 1. That's the way you are getting beta.
Okay. Okay. But how come we multiply k by m?
So k by m is, yeah, that's the way that's the way you are right now. Like you will write this one, you will take this row, and then your column is here. You will take mth column, you will multiply this row with this column, then you will get here.
Okay.
This beta. Okay. Okay. That's all for today.
One last question is there. You want to take? We will take in the next session, is it?
Yeah. Yes. Yes. I will take tomorrow's session.
Okay.
Okay. Okay. Good night to all of you.
Thank you, sir.
Yeah.
Thank you, sir.
Yeah. Good night.
Thank you, sir. Sir, kiss result is released.
No, I think it is not released till now. No. Maybe tomorrow. I'm not sure.
Okay, sir.
Tomorrow probably, I think. For other courses, quiz 2 is released?
Yes, sir.
So maybe probably tomorrow. Yeah. For maths one tomorrow, maybe. Yes, I think so.